Alrighty, everybody. I just got the okay to start our planetarium show, so I'm gonna put away our space trivia questions and that important message because now we're gonna be heading into the unknown. Ooh. And good afternoon, everybody. Welcome to the Morrison Planetarium. Really quickly, I just want to introduce myself. My name is Christian. I'm gonna be your planetarium presenter. And just a heads up, I'm not just a voice coming out of the walls. I'm actually a person, and I'm standing right behind you. Hey, how's it going, everybody? Hee hee hee. Don't hurt your necks. Look forward into the dome before you. Everything that you see there is going to be the entire show. So everything that you see in purple, and I'm very excited for y'all to join us for the last planetarium show of the day here at the Morrison because this is by far my favorite show to present because this one's called Tour of the Universe. And essentially, with Tour of the Universe, we're going to be starting off pretty close to Earth and we're going to be zooming all the way out to the very edge of the observable universe. Hopefully, by the end of the show, you won't have an existential crisis of where we are in space. But just to forewarn you, we are pretty small in the grand scheme of things. So just a heads up. And before we get started with our show, I do have to go over some quick house rules just so that we're all on the same page and have a great experience in the planetarium. There's a few of us in here right now. First off, there's no food or drinks allowed in. If you manage to bring any snacks, make sure those are put away till the end of the show. We want to make sure our theater stays as clean as possible for all the guests coming in the future. We have some things going on tonight. And also, if you happen to have any 21st century gadgets like cell phones, smartwatches, tablets, anything that produces really bright white light, now is the perfect time to turn them off, deactivate them, put them away for the next 30 minutes, as these are very distracting, not only for you, but for the folks sitting behind you, because this room is going to get quite dark. Having really bright white light really takes away from the planetarium show. Also, folks, if you do need to exit early during our show, you're more than welcome to do so. All we ask is that you exit at the very top of the planetarium. That's where you're going to find the exits before, during, and after the show. So when in doubt, always make your way up the stairs, not down them. And last but not least, this show is quite immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you start to get a little space sick, there's a really quick and easy way to ground yourself. All you got to do is close your eyes, take a few big deep breaths, and your brain will remember that you're sitting in a planetarium in San Francisco and not flying across the universe, at least not more than the usual. Hee hee hee. But with that being said, it looks like we're ready to go. So I invite y'all to sit back, relax, and let's begin our tour of the universe. Alrighty, folks, so I'm grabbing controls again, and we're going to be starting off a little bit above our planet Earth at this really cool spacecraft called the International Space Station. We can see the city lights on Earth just down below, but again, we're starting off at this really cool spacecraft called the International Space Station, or the ISS for short. And a lot of people tend to ask me, "Hey, Christian, what is the International Space Station? I hear about it all the time in on the news and articles, but I don't really know what it is. Could you explain it for me?" Well, of course, folks. The International Space Station is a collaboration between many nations all across the Earth, and pretty much what they wanted to figure out is what happens to things in space. So the International Space Station is a research facility, a laboratory that orbits around our planet Earth. And they conduct all different types of science experiments up here. Some of them being, like what happens when you try to grow plants in space? Do the plants grow the same? Do they grow differently with less gravity? What happens when you try to spark a match in space? Does the flame act the same? Does that act differently with less gravity? And one of my favorites is where they had two identical twins. One twin lived on Earth for about a year, the other one lived on the International Space Station for a year. After that year, they compare and contrasted. Turns out when you live in space for a long period of time, you tend to lose a lot of body mass because you don't have gravity constantly working down on your muscles. So if you're planning to live in space for a long period of time, remember to exercise daily. And also, folks, the International Space Station looks enormous on our screen right now, but it's not that big in actuality. It's only about the size of an American football field. So if you've never been to an American football game, don't worry. You can also use the entire California Academy of Sciences, the museum that we're sitting in right now. That's about how big it is. And what's also really cool is that this thing is going incredibly fast. The International Space Station's orbiting around our Earth at a whopping 17,000 miles per hour, where it orbits around the Earth once every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also, folks, the International Space Station looks really far away above our planet Earth, but it's not that far in actuality as well. It's only about 225 miles above the surface of our Earth. 225 miles, that's like going from San Francisco to Santa Barbara, a nice little road trip with the family to get away with for the weekend. So not too far. But 225 miles is as far as we put humans into space nowadays because traveling into space is quite costly. First, you have to build yourself a rocket ship or buy yourself a rocket ship. And then you have to account for all the rocket fuel. You're going to need a lot of rocket fuel. And once you get your hands on all that rocket fuel, you have to account for all the food, water, all the air you're going to be breathing while you're up here in space. So the bill starts to get quite costly quite rapidly. But let's leave the International Space Station because this is just our first stop on our tour of the universe. So we're going to start to see it slowly disappear compared to the Earth down below. And we're going to lose it to the city lights. Looks like we're hovering just above Saudi Arabia, close to the Mediterranean Sea. And before we lose sight of the International Space Station, I want to add a nice little orbital path so we can keep track of it as we continue zooming out. Alrighty, folks. So now we zoom so far out, we're looking down on our planet Earth. And just to let you know, the space program that I'm using here in the planetarium is something that you can go home and download if you like and fly through space, just like how I am. The space program that I'm using is something called OpenSpace. So go to your favorite search engine, type in OpenSpace project. You'll find where you can download it. But just a heads up, folks, this program is in its beta phase, which means that we may come across a few bugs and glitches. If we do, I'll point them out, and hopefully we can look past them. And also, folks, OpenSpace uses a whole lot of processing power. So if you have an older computer, I wouldn't recommend downloading it. It may overwhelm that computer. But if you got something new or a gaming computer, give it a try. It's a whole lot of fun. And also, if you don't want to download anything, kind of like me, I just want to go to fly through space. Well, we also have another great program alternative called NASA's Eyes. So just like the human eyeball, type in NASA's Eyes, and you don't have to download anything. You can just fly through space, just like how I am. But let's leave our Earth behind because now we're going to be making our way over to our nearest natural neighbor to us in space, the Moon. Alrighty, so just to let you know, folks, we humans have been to the Moon before, but that was quite a while ago. That was between 1969 and 1972, thanks to NASA's 6 Apollo missions that brought a total of 12 incredibly lucky guys to walk on the surface, conduct science, and of course, they had some fun up here as well. They got to play some golf. And also, luckily, we're inside the planetarium, so I want to turn off the nighttime on the Moon so we can see everything in all its glory. There we go. That looks much more familiar. But again, folks, the last time we sent humans to the Moon was 1972, a little more than 50 years ago or so. But don't worry, NASA has a new mission in the works that's going to be sending humans to the Moon in the next few years. This new mission is called Artemis. And with Artemis, NASA wants to send humans to Mars. But before we send humans deep into our solar system, we need to figure out exactly how we're going to live out here in space. So the Moon is the perfect stepping stone to figure out all the logistics of how we humans are going to live out here in space. And what's also really cool with Artemis is that they're going to be sending the first woman to the Moon. But not only that, they're also going to be sending the first person of color to the Moon. But not only that, they're also going to be setting up lunar bases throughout the Moon. Pretty much our technology has improved in the last 50 years, so we can conduct much more science in a much more compactable size. And one place that we definitely want to go set up a lunar base is in the South Pole of the Moon. We see lots of evidence of frozen water, of ice, just below certain craters and areas there. And we can use that ice for propelling rockets or splicing that and making oxygen. So there's a lot of use when you can find ice on another world millions of miles away. But again, we should be sending humans in the next few years to the Moon, so look out for any news about Artemis. And folks, when you look up at the Moon here on planet Earth, sometimes the Moon feels so close to you that it feels like you can reach out your arms and touch it. But the Moon is incredibly far away from us. It's about 240,000 miles away from the Earth. 240,000 miles. Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the Moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it, the roads out here are poorly maintained. And from here on out, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everybody say, bye-bye, moon. See you later. And on our journey, folks, we're going to be stepping out into a much larger realm of our solar system because now we're going to watch the moon and the Earth in their orbits as they slowly disappear. In fact, I want to add some nice orbital paths so we can keep track of it because you can easily lose stuff out here in space. And folks, on our journey today, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And just to let you know, folks, the sun is also incredibly far away from us here on Earth. So again, we're the third rock from the sun. So we can see 1 planet, 2, 3, that's us. And the distance between the Earth and the sun, it's about 93 million miles between us. Whew, 93 million miles, that is a good distance away. But in terms of light speed, that's not that far at all. In order for sunlight to travel that 93 million miles at the speed of light, it only takes light about 8.5 minutes to cross that distance. That's not that far at all. And that's a really cool concept to keep in mind because let's say the sun was to turn off all of a sudden. Well, that last bit of sunlight will travel at 93 million miles, that 8.5 minutes at the speed of light. And then all of a sudden, the daytime here on Earth would become nighttime. And again, this is such a cool concept to keep in mind because this works for really far away objects as well. Let's say we're looking at a star that's 70 light years away from us. Well, we're looking at that star as it looked like 70 years ago because that light that just reached us traveled 70 light years to get to us. So when we look at really far away objects out into space, it's like looking back in time in a sense. Pretty cool. But now that we have a nice bird's eye perspective of our solar system, let's do a quick refresher of what's inside of it because there's a lot of good stuff in here. Right in the middle of our solar system, we have our star, the sun. The closest planet to the sun, we've got Mercury. Then we have Venus, Earth, Mars. These are the rocky terrestrial planets. These are places where we can actually land a spacecraft on. And then past the orbit of Mars, we have this really cool thing called the main asteroid belt. And this is what it would look like if we were to highlight all the asteroids in our asteroid belt. There is a lot of them. And then past the asteroid belt, we have the really big planets, the gas giants. We've got the Jovians. We've got Jupiter and Saturn. And then we have our icy gas giants. We got Uranus, the funny one, and Neptune. And of course, we can always add everyone's favorite and lovable dwarf planet, Pluto. So here's the orbit of Pluto up on screen, just down below. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt, past the orbit of Neptune. And you're probably wondering to yourself, what's the Kuiper Belt? I've never heard of that before. Well, folks, the Kuiper Belt's going to be all this stuff. So again, we are now looking at the Kuiper Belt, and you can think of it like a second asteroid belt much further away from the sun. And where you're mostly going to find out here are icy asteroids and short period comets that don't stray too far away from the sun. And the reason why we kind of just came about this is because in 2006, our technology has improved a lot since then, and we're able to see much more smaller objects, much more distant, much further away. So as we're constantly scanning the night sky, and our technology is improving, we're able to find more stuff much further away from our sun. So that's a really cool thing about science. As we learn new things, we're able to change the way that we see our solar system. But folks, I'm going to put away our Kuiper Belt because that's just a whole lot to look at. And right now I'm going to be adding on screen some of the many different spacecrafts we sent out in the 1970s to explore our solar system. So on screen, we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. We're able to see this interaction right over here. So that's New Horizons that did a quick flyby. And just to let you know, all these spacecrafts are traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventurers, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, takes sunlight about 5 hours at the speed of light. Only 5 hours. That's not far as well. But folks, let's leave our planetary system scale behind because now we're going to be heading out into interstellar space, the space between the stars. Distance now becomes so immense it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And if my calculations are correct, Alpha Centauri is going to be the star system closest to us on the left-hand side right there. So again, 4 years at the speed of light just to reach the next star system, but that doesn't really put into perspective how long it would take us to travel that distance. Well, if you're to get in a rocket ship, left Earth right now, headed over to the next star system, it's going to take you about 8,500 years to cross that distance. And that's just a one-way trip. Whew. But folks, let's stop and consider whether humanity has made its presence known beyond our solar system, because now we're going to be stepping inside something called the radiosphere. And once again, folks, we are now inside the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted or rather leaked into space. And it extends about 90 light years, emitting it from all directions from the Earth. And this began in the early 1930s with strong radio waves, early television, radar signal, and then later the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that, but the radio signals back then, the electromagnetic signals, weren't as powerful to escape the Earth. And since all these signals are electromagnetic, they are traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is expanding at the rate of 1 light year per year. So is anybody out there listening? And right now, folks, I'm going to be adding on screen some many different markers. These markers represent some of the many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found 5,000 exoplanets confirmed in our nearby vicinity to us, 5,000 other worlds besides our own. And that 5,000 number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. Now, to say if any of them are Earth-like with conditions suitable for life as we know it, well, we can't answer that question quite yet. Pretty much new spacecrafts or space telescopes are being developed right now, so it's going to be a few years before those are made and then launched into space and then, of course, conduct science. But the more important point here is that quite a few of these planetary systems are within that 90 light-year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we live in a star system on the far left of our radiosphere. Let's say this one right here. We find an alien civilization somewhere towards the middle. Let's say that. We shoot them a text message, takes 60 years to get to them. They listen in, answer back, another 60 years to get that message. That is a 120-year conversation in the making. Whew, and I could barely wait for a text message from my friend. But of course, folks, planetary systems beyond our radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And for now, I'm going to put away our exoplanet markers. I'm going to leave our radiosphere up on screen because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way Galaxy. So keep your eyes on it. Alrighty, folks. So we're now looking down at our Milky Way Galaxy, and can anybody see their house from here? Just kidding. So our Milky Way Galaxy is incredibly large, folks. If you wanted to cross it from one side to the other, it's going to take you about 130,000 years at the speed of light to cross it one way. Whew. And not only that, our Milky Way Galaxy is so huge, we estimate that there's at least 300 billion stars in our galaxy alone. If our recent discovery of so many exoplanets just within our small neighborhood within this vast star city is any indication, there could be potentially billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And before we leave our Milky Way Galaxy, I do want to show you what it looks like from a sideways perspective. You're going to notice that we live in a flat spiral disk of the Milky Way, and it looks like a pancake from a sideways perspective. And you probably heard someone say when you look up in the night sky, hey, look, you can see the Milky Way. What they're referring to is this, the Milky Way plane. So this is what you're seeing up in the night sky. And keep this in mind because when astronomers and scientists want to learn about the universe, it's a lot more easier for them to point their telescopes galactically north and galactically south instead of looking through the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So again, keep that in mind. That's going to come important later on in the show. We like to point our telescopes galactically north and galactically south. But folks, the Milky Way Galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group, which contains about 30 galaxies, large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And folks, as we continue zooming out, you're now going to realize that galaxies are not evenly distributed throughout space. Instead, galaxies like to clump together in large groups and clusters. So we can see a nice group over here, a cluster over there, a cluster over here, or they like to avoid each other where there's very few galaxies or no galaxies at all. So you can see very few galaxies right towards the top of our planetarium and no galaxies at the very top. You can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And folks, the picture that we're looking at represents the closest 30,000 galaxies over a space over 300 million light years across. We got to give thanks to an amazing team of astronomers that worked at the University of Hawaii who compiled this amazing representation over decades of time. So big shout out to that team. I love flying through this galactic map. But folks, we now have automated systems that are mapping even the most distant galaxies. Folks, we're about to see the very large scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. Whew. And also, just a heads up, the large-scale structure of the universe is not shaped like a bow tie or a butterfly. As we start to spin around, you're going to start to see that shape. There we go. Remember when I mentioned that we live in a flat spiral disk of our Milky Way? Well, if we were to line up our Milky Way galaxy, it would line up just down in the middle, just like so. So again, we like to point our telescopes galactically north to find things and galactically south. But astronomers still want to look through the plane of our Milky Way to find galaxies. You can see this nice purple survey right in the middle. You'll notice that they were still able to find galaxies, just not as far and not as many. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to map out all of these areas that haven't been mapped out yet. So you can kind of think of all these galaxies, but in every direction that you look. So it's just a matter of time before we map it all out. But folks, it looks like we're running close out of time on our 30-minute tour of the universe. 30 minutes is just not enough time. So let's continue pressing on, because now we're going to be coming across these really far distant objects known as the quasars. And the quasars are short for quasi-stellar radio sources, which are going to be labeled on these nice orange dots at the very edge of the large-scale structure. We got some quasars over there and over here. And folks, these objects are billions of light years away, so now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe, and before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. Alrighty, folks. So here we are at the very edge of the large scale, or at the very edge of the observable universe, and what we're looking at is something called the cosmic microwave background image, or the CNB image for short. And all evidence indicates that the universe we live in is about 13.8 billion years old. And this is data compiled by Planck and other radio telescopes. And the picture that we're looking at is the very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And what we're looking at is not a typical photo either. Instead, this is a temperature density image where the light echoes of the Big Bang are color-coded, with the lighter areas corresponding to the hottest, least dense regions, and the darker areas the coolest, densest regions. These fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But eventually, they gave rise to that large-scale structure of the universe, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've reached the very edge of the known universe, so we only have one direction left to go, which is going to be back towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make a return trip back to Earth. And folks, we're crossing an expanse of 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. Now, we live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. With that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to peer into their telescopes and see into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we're just entering our Milky Way Galaxy, folks, making our way straight for that radiosphere. And of course, we're making our way downtown, walking fast, faces past when we're homebound. Dun-dun-dun-dun-dun-dun. And we're now approaching our star system, folks, our solar system. And we're now about to pass the spacecrafts we sent out in the 1970s, passing the Kuiper Belt and the orbit of Pluto, passing the main asteroid belt, and making our way to the third rock from the sun, our home world, planet Earth, the only place we humans have ever called home. And it looks like we're about to pass the orbit of the moon, the furthest we've ever sent humans out into space. And as we make our final approach back to planet Earth, folks, this is going to be the end of our Tour of the Universe show. And I want to thank you all for stopping by and watching it with us today. I hope you did enjoy it. But hey, look at that. We made it back home safe and sound. And that's all for today, folks. Thanks for stopping by.